Good evening. Am I audible?
Yes, ma'am.
Good evening.
Yes, ma'am.
Okay. Good evening.
Yes, ma'am.
Yes, Swati, are you there?
Yes, ma'am. I'm there. Are you able to hear me?
Yes. Yeah. So, do
Yeah.
you want to start it and then I can take it from there?
Just a second. I'll just tell them some instructions and then you
Sure.
can start.
Yeah. Right. Thank you. Is my screen visible?
Yeah. Your screen is
Yeah.
visible.
Okay. Right. Thank you.
Okay. Hello, guys. Today's revision session will be taken by Usha, ma'am. So in today's lecture, we will be only clarifying the conceptual doubts, and your general doubts and assignment-specific questions will be taken later by the instructors. Okay. So please be disciplined and please cooperate. Okay.
Thank you. Thank you all. And thank you, Swati. As
Welcome.
Swati mentioned, the purpose of today's session is to just revise the concepts of permutation, combination, and probability. Probability right from the definition of random variable up to the base theorem. Every time we have such a revision session, as again rightly pointed out by Swati, there are very specific questions, and these questions are related to the assignments. These questions will not be discussed in the revision. Only any clarification at a conceptual level we are going to clarify. I hope it is clear to all of you. Okay. And to maintain decorum, I will talk about a concept. I'll pause for questions and then you can ask me questions. Okay. Because we have just 2 hours, and in this 2 hours, I do have a whole lot of things that we want to cover. As you can see, the topics that we want to cover is starting right from the basic principles and goes up to probability trees. So to be fair to the agenda, I think after every topic, I'm going to give 5 minutes or 3 minutes to clarify. Okay. I hope this is okay. Meanwhile, you can also use the chat box to raise your questions. I will go through the chat box, or Swati, you can also just consolidate the questions that are being asked in the chat box. And if I miss on answering anything, you can let me know later.
Yes,
Is this
ma'am.
clear to all? Yeah? Okay. So what is the agenda for today is, as I mentioned, that we are going to review the conceptual understanding of key, the permutation and combination, what is probability, and what are properties of probability up to base theorem. So let's start with the basic principles of counting. When we talk about basic principles of counting, there are 2 basic principles of counting. One is what we say is the addition rule of counting, and one is what we say the multiplication rule of counting. Now, when we are talking about the additional rule of counting, the thing that you need to understand is addition rule is if something can occur in n1 different ways, that is A, an action A can occur in n1 different ways and B can occur in n2 different ways, the total number of ways of A or B to occur is n1 plus n2. Similarly, in the multiplication, if an action A can occur in n1 different ways and B can occur in n2 different ways, the occurrence of A and B together is n1 into n2. So that can be best illustrated by the example that you can see on your screens. For example, in the first bullet point, my question is, I have 3 shirts available to me. I have a yellow shirt, an orange shirt, and a green shirt. And I have 2 pants, which is a black pant and a blue pant. If I tell you to choose either a shirt or a pant, I repeat, if I tell you to choose either a shirt or a pant, you'll end up choosing either a yellow shirt or an orange shirt or a green shirt or a black pant or a blue pant. So the total number of ways to do it is 3 ways I can choose a shirt, 2 ways I can choose a pant. So I add this to come to a total of 5 ways. On the other hand, if I ask you to choose a shirt and a pant, for every shirt, I can have a pant chosen. So if I choose a yellow shirt, I could either pair it with a black pant or a blue pant. If I choose an orange, I can pair it with either a black pant or a blue pant. A green shirt, I can pair it with a black pant or a blue pant. So if you can look at the tree structure, you can see that the total number of combinations available here is this is 1, this is 2, 3, 4, 5, and 6. The key differentiator is when we talk about addition, it is an OR operation that we are taking into consideration. Whereas when we are talking about multiplication, it is an AND. So whenever I talk about A or B, it is addition. Whenever I talk about A and B, it is multiplication. Now this multiplication rule of counting, I can extend it to many other items. So if there are R actions that are performed in a definite sequence, there are N1 possibilities of the first action, N2 of the second, then the total number of ways of doing it is N1 into N2 into NR, the product of these many ways of doing it. This multiplication rule of probability helps us introduce what is called the factorial notation. What is the factorial notation? If I have n blanks, then there are n ways of choosing or filling up the first blank. Given this, that I have filled up with one of the n ways, there are n minus 1 left for filling the second, n minus 2 the third, and so forth. So n into n minus 1 into 1 is the total number of ways, and this product of the first n positive integers is what is referred to as the factorial, and it is denoted by n factorial. By convention, 0 factorial is equal to 1. Now, given this, this is the basic law, and how do we use this basic law in establishing permutation and combination? I'll take a short break here. Any questions with the addition rule and the multiplication rule leading to the factorial notation? Please ask me. Any questions? Is it clear?
Ma'am.
Yeah, please go ahead. Yeah, hello?
Yes, ma'am. For in the addition rule and the multiplication rule,
Yeah.
we are going to have a number of ways, or we are going to have the probabilities over there.
There's no probability. This is just the basic rule of counting. We
Okay.
need the basic rule of counting because when we are talking about probability, we are again looking at a count, right? Number of ways an event can happen. So we are going to use these concepts. These are building blocks. We call for any mathematical concept, we have what are called building blocks. So these are the building blocks which are leading us to the probability. This is just basic laws of counting, principles of counting. Okay.
Yeah.
We have still not introduced the notion of probability here. Any other questions?
Yes. No, ma'am. Got it.
Okay.
Thank you.
Excuse me, ma'am.
Right. Yes,
In
please.
case of we want shirt or a pant, it can also include the case like shirt and the pant because it is or.
No.
Is it?
Shirt or a pant cannot include shirt and a pant, right? Shirt or a pant is either you choose a shirt or a pant. Imagine you're given a coupon, right? Or some discount coupon which says that you can use it for a shirt or a pant. You cannot use it to buy both shirt and a pant, right?
Okay, ma'am.
You get it? So that's why there are only suppose I give you a discount coupon of say 25% discount coupon to go to a retail store, and I say you can buy it to buy one shirt or a pant. Okay, there are 3 shirts available to you and 2 pants available to you. How many ways do you think you can use that coupon? 5 ways, right?
Yes, ma'am.
But if I give the same coupon and say that you can use for a shirt and a pant, I'm not saying 2 shirts. 2 shirts is not allowed here. So in that way, you can use it in 6 different ways.
Yeah, okay, ma'am.
Right? That is what. How do we use it in probability? What is the chance of you buying a orange shirt and a blue pant? That is where you can use this notion of basic counting is where you're using it in probability also. Is that clear? But I first need to have the building block of how do I count? And these are the 2 key principles of counting. Is it clear?
Yes, ma'am.
Okay, right. So with this basic conceptual understanding, we introduce the next important concept, which is that of a permutation. So what is a permutation? A permutation is defined to be an ordered arrangement. Now these are very, very important, ordered and arrangement. For example, if I take 3 people, A, B, C, and I am going to ask them to sit in 3 chairs, I can make them sit either A, B, C or A, C, B, or BAC, BCA, CAB, or CBA. These are the ways they can be arranged. You can see that each one of them is a distinct arrangement. Is this clear? Okay, this is a distinct arrangement. And it actually, you can see that even though all the three arrangements, you have A, B, C, here B is to the next of A, here also B is to the next of A, but A is occupying the first chair, here A is occupying the second chair. So they are different. So permutation is an ordered arrangement of sum or all. What do we mean by sum or all? Suppose I had D also, and I'm looking at choosing, ordering 3. That is, I have only 3 chairs. In which case, how can I order? Again, I can have ABC, I can have an ABD, I can have an ACB, I can have an ACD, and so forth. It's going to keep increasing because I have only 3 chairs and I have 4 people whom I can sit in these 3 chairs. So this is the idea of permutation. In particular, this is a linear permutation because I am arranging objects in a linear fashion or in a line. The concept or the differentiator here is because very soon we are going to introduce the concept of circular permutation. But now we are only talking about linear permutation. So when I talk about linear permutation, for example, I have R objects. So I have 4 people. How many ways out of these 4 people, let me call them A, B, C, D. The first chair, how many ways can I fill up this first chair? How many ways can I fill up the first chair? How many people?
4 ways.
4 ways.
4 ways.
4 ways. Either A can
4
sit,
ways.
or B can sit, or C can sit, or D can sit. So I can fill it up in 4 ways. Now, given that one of them has sat here, how many ways are remaining to fill this? Second chair. 3.
3.
3.
How many ways can I fill this third chair?
2 ways.
2 ways.
2 ways.
So you can see that this is the multiplication law, the principle I'm using here, because I'm saying I want to fill this chair and this chair and this chair. There are 4 ways of filling the first chair. There are 3 ways of filling the second, 2 ways of filling the third. So the total number of ways all the 3 chairs can be filled is 4 into 3 into 2. Okay. Now I can, pardon? Okay. Now I can extend this here. If this 4 is what I say n objects and 3 was R, I can extend this objects to the number of possible permutations of R objects from a collection of n distinct objects. So R objects, I now have R chairs, the first way, and I have n objects. First, how many ways can I fill the first one? If I have n objects and I have to fill R, n ways. The second,
N minus
N minus
1. Second and third is n minus 2.
N minus
And the
2
last one is
and
n
fourth is
minus
N
R
minus
minus 1.
3 and
Okay. So again, using the same thing, the number of ways I can permute or the number of possible permutations or the number of possible arrangements of R objects from a collection of n distinct objects is n into n minus 1 into n minus R plus 1. This is the first key result. Now this is denoted by NPR, P standing for permutation. Okay. Now you can see that this first one, I can write this as n into n minus 1. I can just write it as okay. So you can see that this I can write this as n into n minus 1 into n minus r plus 1. I can multiply and divide this as n minus r minus 1 up to 1. I can do the same as n minus r minus 1 up to 1. You can see that this is nothing but n minus r factorial, the denominator. The numerator is n factorial, which gives me the identity that this NPR is nothing but n factorial divided by n minus r factorial. So this is the primary thing that we are setting up, which is called the number of permutations of R objects. Again, these objects are distinct. You should be very careful that these objects are distinct. Repetitions are not allowed. Then the number of permutations of R objects from a collection of n distinct objects is given by n factorial divided by n minus r factorial. Here, we also know that 0 factorial is equal to 1. We have established that. So you can see that NPO is equal to 1. NP1, how many ways can I choose one object from n objects? There are n ways of choosing. So NP1 is n. NPn is equal to n factorial. That is, I can arrange n distinct objects in n factorial ways. So this is the first way or the first formula of permutation. Now, what would happen if repetitions are allowed? That is, the objects are distinct, but repetitions are allowed. Now, typically, repetitions are allowed. Now, this is the kind of problems that you will face where you are asked at how many ways can I generate a passcode, a 4-digit passcode. Okay. Now, in a 4-digit passcode, if I allow 0 also, how many ways can I fill the first one?
Y into
10 ways.
10 ways, right? 0, 1, 2, 3, all. So 10. How many ways can I fill the second one? Repetitions is allowed.
10 ways.
10 ways.
10 ways. Third way is again 10. Fourth is again 10. So the problems which come to you where repetitions are allowed. So you can see that. But now suppose I tell here that it cannot start with 0. I'm just modifying the problem. It cannot start. You cannot start a number with 0. Then what would be the number?
9,000 into 10 into 10.
Will be 9.
And plus 10 ways.
First digit
Only
will
the
be 9.
starting number cannot be 0. How many ways can I do the next?
9 into 10 into 10.
10
9
ways.
into 10 into 10.
ways.
Is this
10
clear?
ways.
So
Yes, ma'am.
depend. You should know whether I should use it. So when would you use NPR, a quick check, and n to the power of r? Both are filling up r objects from a collection of n distinct objects. What is the key difference between this formula and n to the power of r?
Repetition.
In this case, you are allowing repetitions. In this case, you are not allowing repetitions. Is this clear? However, these n objects are distinct. So far, so good?
Yes.
ma'am.
Yes,
Yeah.
ma'am.
Yes, ma'am.
Okay.
Yes,
Now the
ma'am.
next thing is you would have seen problems like, okay, I am giving you a word statistics. Okay. How many alphabets I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm having 10 objects here. My n is equal to 10. But what is the difference between this and the earlier thing? What is the key difference? Are
There is
all the
repetition.
alphabets
Addition of digits.
There are alike objects.
They are not distinct. Is it
Not
clear? They
Yes.
are not distinct. So
Yes,
when
ma'am.
they are not distinct, what is the problem when they are not distinct? When they are not distinct, for example, if I have DATA, right? Whether I'm putting this A1 and A2, suppose I'm taking DA1, TA1, A2 and DA2, TA1, they are the same, right?
Yes,
Is it
ma'am.
right? Okay.
Yes, ma'am.
So when the objects are not distinct, I need to account for the way that they are arranged among themselves. I repeat, when the objects are not distinct, I need to account for the way they are arranged among themselves. So what does that mean? That these two arrangements are the same. So I need to divide by the number of ways I can arrange them. And that is, 2 of them are distinct. So I need to divide it by 2. If 3 of them are distinct, how many ways can I arrange? Suppose it was A3 also, it would have been 3 factorial ways. Would you all agree? Yeah?
Yes,
So
ma'am.
this
Yes.
n fact, where p of them are of one kind is n factorial by p factorial. I can extend that when I have p1 of one kind, p2 of one kind, and pk of the kth kind is n factorial by p1, p2, pk factorial. Someone raised their hand. I'll just
Excuse
stop
me,
for a
ma'am.
minute. Yeah.
Just one query.
Yeah.
This formula permutations, when objects are not distinct, we are not considering repetition of the object, so we are doing n factorial. But in the case where repetition is allowed and still there are not distinct objects, so so can we use this formula like n to the power r and then dividing by the factorials which are alike?
I didn't get your this one. What can you please repeat?
Means when we are permuting, suppose the repetition is allowed, and in that case also I have suppose P1 alike objects and P2 alike objects of another kind. So in that case, can we use the in the numerator there will be the exponent, and in the denominator there will be the P1 factorial, P2 factorial, that kind?
Yeah. See, because I think I get your point. So you're saying that can I have an SSS? Is that right? If I'm going to if I want to make a word of 3, right? From statistics,
Yes.
that's what you're asking, right?
Yes.
Okay. So suppose, let me tell you, if I put S1, S2, S3 here, agreed? And I
Yes.
put a T1, T2, T3, okay? And an
Yes.
I1, I2, right? Now I have 10 distinct. Is that clear?
Ma'am.
Is that clear? Now I
Ma'am.
have 1, okay, S1, S2. That totally I'm treating everything as distinct objects here. Is that clear?
Ma'am.
Hello?
Ma'am, clear. Yes, ma'am.
Yeah. So now, in that case, this S1, S2, S3 is allowed because I'm having S1, S2, S3. I'm treating it as distinct objects. Is that clear?
Yes, ma'am.
Right. Now, but this S1, S2, S3 is same as S2, S1, S3, which is same as S3, S2, S1, and all the 6 permutation is the same.
Yes, ma'am.
Agree? So I'll have to divide it by this P1 factorial or by this P factorial because they are all distinct. Till here, is it clear?
Yes, ma'am.
Right. So now let's take a simpler word, which is DA1, okay, data. Okay. Now suppose the question you're asking is, suppose I am taking Swati, is it compulsory?
Sorry, ma'am.
Is it compulsory to attend the session? One person has asked.
No, ma'am. Actually, that girl, she is having doubts in week 8 only. So that's why she is asking, like, can
Now, I
she?
cannot say whether I'll exactly start anything in week 8, okay? So you can just meditate for 1.5 hours or 1 hour, and whenever I start, you can ask the doubts, okay? I cannot say that it is week 6 is not from 6 to 6:30. Week 7, it doesn't work that way. It could start sometime around 7:15 also, okay? So you can join whenever you want, not an issue, okay? Right. And if you have any administrative question, you please ask. Box, and I don't want anything which is outside the class, this one to happen. Okay, right. Okay, so now with this DA2, okay, so I could have an A1, I could have a because I'm repeating it, right? I could have A in both the cases, but A1 is same as A2 also. That's what I'm trying to say. Okay, in that case, I need to look at repetitions allowable, and I should account for all these factorial things also. Is it clear? So the numerator would be n to the power of r, and I need to divide by whatever is going to be repeated. You just work out for a small example, you'll get the answer.
Okay, ma'am. Thank you, ma'am.
Yeah. So now, when we talk about linear permutation, the 3 key things are when the objects are distinct, repetitions not allowed. Objects are distinct, repetitions allowed. Objects are not distinct, then how do I look at it? These are the 3 key ideas. And based on the problem, you need to see whether I need to apply the repetition allowed, repetition not allowed, or whether they are non-distinct objects, depending on the problem. The other important thing that you need to understand in permutation is about what we call circular permutation. Now, what is a circular permutation? As I said, so far we are interested in arranging people in a linear fashion or in a line. But most of the problems, again, you'll see that people are sitting in a round table. So when people sit in a round table, what happens is, as you see, in this, whatever we have demonstrated here, A, B, C, D is one way. Okay, here A is next to B is next to C is next to D. But you can see that this would be the same as B, C, D, A. Again, A is sitting next to B, B is sitting next to C. This is the same. These two are same. Would you all agree with me?
Yes, ma'am.
Yes.
Yes, ma'am.
Which is
Yes,
again
ma'am.
the same as C, D, B, A. Okay. So what is happening is whenever I talk about a circular permutation, I should not treat these differently. Now, in order to not treat this differently, what we do is we fix one of them and we treat the other as a linear permutation. Suppose I fix A, okay, and I'm saying, okay, I want the others to be seated in a line, and then I'm saying that, okay, I'll finish the loop. So if I fix one of them, how many ways can I arrange the others? I can arrange them in 3 factorial ways. So here I have fixed A, and you can see that among B, C, D, I can arrange them in 6 factorial ways. So I have 6 ways of arranging it. Now here again the clockwise and the anti-clockwise are different. So I need to, so if they are the same, then this A, B, C, D is the same as A, B, C, D. These two are the same. If the clockwise and anti-clockwise are different, the number of ways this n objects can be arranged in a circle is n minus 1 factorial. However, if they are same, what do you do? Because if this is same as this is same as this is same as this, what happens? You'll have to divide the number of factorials, and that's why I get n minus 1 factorial by 2. So this is another important concept. Whenever we talk about permutation, understand whether I have distinct objects, understand whether you have to do first of all, understand whether it's a linear permutation or a circular permutation, depending on what is your question. If it is a linear permutation, check whether the question is telling that the objects are distinct or they are not distinct. If they are distinct, check whether repetitions are allowed or not allowed. If they are not distinct, you have the formula. If it is circular, again check whether the clockwise and anti-clockwise are the same or whether they are different. If they are the same, apply the formula for same. If they are different, apply the formula for different. Any questions so far?
Ma'am,
Yeah.
ma'am, if the question is saying that instead of fixing one, we have to fix 2 or 3 elements in a circle permutation, then what will be the formula?
So let me ask you the same thing. I want to fix 2 now. Okay. So what would be your way? So here initially I fixed 1. Okay. This is the plain basic case, right? So if I have to fix 2, what would you do first?
Ma'am, first I will select the 2.
Select the 2. And how many do you have remaining then?
Ma'am, other 2.
Other 2. Between those 2, how many ways can I fix? So I'm going to talk about it as a block, right?
Yes,
Is
ma'am.
it clear? And among them and within them, how many ways can I arrange? That also you can see. Again, you need to do whether it is clockwise or anti-clockwise. Is it clear?
Ma'am, means after arranging, we have to multiply by the factorial. Means if we have fixed 2, then 2 factorial will be multiplied.
Yes. Yes. Again, depending on whether clockwise and anti-clockwise are same or different. Is that clear?
Yes.
Because if I fix, is that clear? Right? Because
Yes.
AB and BA as a block, right? That is what I need to check. Is that clear?
Yes.
Yeah. Any other questions?
Yes, ma'am, I have a doubt.
Yeah.
Can I? Yes, ma'am, instead of you considering 4 people, you are just considering of 10 or 11, a huge number. 2 persons are interested to sit beside each other.
Next to each other. Yes, that's
next
it.
to each
Yeah.
other, and another person interested to sit with along with A in the left hand side. They just given that in this direction means in a specific direction how he should, ma'am.
See, whenever you have problems of that kind, see, for example, you'll have problems that even, let's look at a linear, and then after that same idea will apply. Suppose I have, go back to this question here. I have A, B, C, D. B and C want to be always together. Okay? B and C always want to be together. Then what would happen? I can start by the logic that I can look at B and C as one single entity. Is that clear?
Yes, ma'am.
Now, if B and C are a single entity, how many entities do I have now? in this
Ma'am,
ABCD?
we are having 3, ma'am.
3. Okay. I already know how many ways I can arrange them. How many ways can I do that?
It's nearly
No,
7.
how many ways can 3 factorial, right?
Yeah, yes, ma'am. 3 factorial.
But B and C, how many ways can I arrange between them?
2 ways.
Factorial.
2 ways, ma'am.
2 ways.
So now do
2
you get
factorial.
it? So whenever you are having problems that 2 people are together, okay. Now suppose I'm telling you B and C do not want to be together at all. They are saying they refuse to sit next to each other. Then how many ways do we have?
Total minus together.
Total minus when they are together.
That. Is that clear? So
Yes,
that
ma'am.
is how you, so you are seeing that you start applying the logic of counting to get whatever it is. And as one of you asks, okay, to the left and to the right, then you fix a position and then see how other things work. Is
Yes,
that clear?
Yes, ma'am.
Yeah?
Yes, ma'am. I got it, ma'am.
You got it?
Excuse me, ma'am.
Hello.
Yes. Yeah.
Ma'am, I have a doubt in circular permutation.
Yeah.
As in a question that I was solving today, in a restaurant, 17 men.
Is it an assignment problem?
No, ma'am. I
Okay.
don't know, but I searched for quiz 2 PYQs and this question come in a PDF.
I'm sorry, but I don't think we'll take any specific questions here. Okay, because the specific questions you please ask in this tutorials which will be conducted by Swati and the other instructors. This is only at a conceptual level because I don't want to take any specific question here. Is that clear, please? Okay.
Yeah. Ma'am, can you understand me the topic when we have to make people to be sit between two others and not to be sit between
See,
two others?
everything, for example, if I'm saying that I have A, B, C, D, okay, D and C should not be together. Then you will always work D and C are together, total number of ways minus that. And the same logic which you use for linear, you can use here. Would you all agree? Sometimes they'll say that, okay, B should be to the left of C. Then again, you can do the clockwise and anti-clockwise are not the same and you can use those formula. But the idea is always to try and fix a position and then see how it is. Some problems would say that, okay, B should occupy this seat. You're not allowing B. So you're fixing a seat. Then among the others, how would you look at? All of that, you should try the same way. You can try and apply the formula. That's it. We cannot be doing all the cases here. These are the primary concepts. But for each problem, you can apply these concepts and get the answer. That's what we are trying to say. Is that clear?
Ma'am,
Yes,
I
ma'am.
actually had a doubt.
Yeah.
Ma'am, so like, let's say we're arranging A, B, C, D. There are questions where like these events occur simultaneously or not. Like, what does that mean? Like, so here we are arranging A, B, C, D. Are we like, is the events occurring simultaneously or not?
A, B, C, D. Here we have not introduced the notion of an event yet. Okay, it is just I'm arranging 4 people or 4 balls or 4 items. Okay, events will come when we are talking about probabilities. Okay, is that clear?
Okay, ma'am.
Excuse me, ma'am.
Yeah.
I'm just acquiring the formula of circular permutation. We have understood by the logic that we will fix one element and then permute the rest of the element. That gives the formula n-1 factorial.
See, the idea of that, yeah. See, the idea of that is to understand circular permutation, okay, is to see that when I'm seating people in a table, right, whether it is A, B, C, D, okay, that is A is sitting here, B is sitting here, C is sitting here, or D is sitting here, or B, C, D, A, it's the same. That is the idea, okay. What does that idea say? To the next of A, I have B and D. In both of them, these are the same, right? So to come with a total number of arrangements, I just fix this and permute the other. So in a sense, I'm saying, okay, you fix this and the other I can treat as a linear permutation and then I am putting it. That's why I'm getting the formula for a circular permutation. Now, this is the general formula. There could be problems where you say that 2 people do not sit together, men and women. So they'll say that how how many ways can you seat 6 men and 6 women such that only couples sit next to each other? You have questions of this kind appearing, right?
Yes.
Agreed. So you should view each question in that context. The basic formula is this. That's what I want to say. Is that clear?
Yes, ma'am. The idea behind the basic formula I understood. With respect to this, I have two queries. Means the first query means the example you gave, that arrangement of A, B, C, D in which the BC should be sitting together. So the linear logic I understood. If it was around a circular table, then we should have first fixed BC as a unit. Then we have three elements.
It is not that you should have fixed BC as a unit. You can always fix A. BC would be BC is a unit. It's another unit, so it will be n minus. So this will be A. This would be 2 factorial now. It won't be 3 factorial.
Okay, 2 factorial of the separate elements.
You need to understand whether clockwise and anti-clockwise are same, because whether see A, B, C as a unit with D and A, C, B as a unit with D, this we need to see, these are different, right? A, B, C and C, D. Right?
Okay.
Is it clear? So that is the way I'm trying to say. You need to understand what you're, see, within them, whether the arrangement makes sense or whether it makes a difference. That is what you need to see. Is it clear?
Okay, thank you, ma'am. One last query. When in the question, in the scenario we are doing arranging n objects in a circular permutation way, then with this logic, the n minus 1 factorial formula is coming. But if in the question it is already mentioned that one has to be fixed, then what should be the formula? N minus 2 factorial.
See, if they're telling you which one has to be fixed,
yes.
Okay, then afterwards, depending on that, it would be because that I have only n minus 1 available with me, right? So it would be n minus 2 factorial. But if the choice is I do not know which of the one, then I have a choice of which of the one has to be fixed also. Is that clear?
Okay, okay, thank you, ma'am.
It again is very contextual. See, again, what you need to see is, for example, you see, if I have all distinct, I'm not looking at distinct and undistinct, because you'll have here people sitting in a round table, they are distinct objects. But suppose I am making a garland of pearls and something else. They are not distinct objects, right? Is that clear?
Yes, ma'am. Thank you, ma'am.
When I'm having, say, I'm making a garland. This is also a problem which you encounter, right? So they are not distinct. So that is, we have a different way of treating that circular permutation when they are not distinct. Is that clear?
Yes, ma'am. Thank you, ma'am.
All you need to understand is, if I have only one green and all red stones, these are all red stones, and this is a green stone, right? I fix the green stone, these red stones are not n minus 1 factorial, because there's only one way of putting that arrangement. Remember that. Is that clear?
Okay, ma'am. Thank you, ma'am.
Right? Okay. So this is the,
Ma'am, if it is said as like select random two persons and make it as unit, then we have to take it as NCR, then multiply the factorial of arrangement.
See, again, these are all very contextual. You look at the problem, what is it? First of all, are you asking to choose two people or things like that? So we'll do the combination and we'll look at these problems again if you have the time. Okay? Yeah.
Okay, ma'am.
So the next thing is the concept of combination. In permutation, the key thing that...
Sorry, ma'am. Can I just ask my clarification, please?
Yes.
No,
The last question, in permutation,
permutation only, ma'am. Ma'am, actually, you said that when B and C are supposed to sit together means, I mean, they should be sit near them. Means you said that we should take B and C as a single unit, and A and D will be taken as separate unit, right? So you're saying that the total will be it will be 2 factorial ways. But what if the B and C had internal arrangements between each other? Then what will happen?
What do you mean by internal arrangement between each other? That is, B is always to the left of C or something of that kind.
Yeah, but
you'll have to count it that way. See, for example, if B and C are together, A, B, C, D is one way to seat them.
Yeah.
A, C, B, D is also a way to seat them.
Yes, ma'am.
Okay. Now, B, C, A, D is a way to seat them. C, B, A, D is also a way to seat them, right?
Yes. Yes, ma'am.
So that's why so you'll have 6 factorial, and between them you have each one of them, and that is how you'll keep going. Is it right?
Okay. Okay, ma'am.
Right? Yeah.
This is what I actually asked.
Right. So now let's move on to the next question, and that question, the next concept is that of combination. See, typically you'll be asked questions like, okay, one of the questions that you will always see is, suppose I want to choose 3 people from a class. Okay, that is one of the questions for a committee, school committee. The second question is, I want to choose a president, a vice president, and secretary from a class. I want to choose these 3 people. What if in both the cases I'm choosing 3 from a class of 50 people? Agreed? Would you all agree with me?
Yes, ma'am.
Yes, ma'am.
Both the case. But what is the key difference when I am choosing a president, vice president, and a secretary, and I'm just choosing 3 people for a committee? What is the key
They're
difference?
distinct. They're distinct.
Not distinct. Given when I'm choosing 3 people for a committee, they're
Order.
distinct. There is an order. There is an arrangement. When I'm choosing 3 people and telling that A is president, B is vice president, and C is secretary, is different from A being vice president, B being president, and C secretary, is different from C being president, A being vice president, and being secretary. These 3 are arrangements. They are different. Whereas if I'm just choosing 3 people from a set of 50 people and I happen to choose ABC, there is only one way I can choose this ABC, and that is a combination. There is no order. I'm just choosing 3 people. Do you see the key difference in this?
Yes, ma'am.
Yeah?
Yes, ma'am.
So in this, so when the order is not important, so in questions you'll always find, is the order important? Is the order not important? When the order is not important, it is not an arrangement, it is just a combination. It is a choice of 3 people. We call it a combination. Okay? And how do we represent it? We say that the number of possible combinations of R objects from a collection of n objects is denoted by n choose R. You already know that this n factorial by n minus r factorial is npr. This is something which you already know from our earlier discussion, right? Now, each of this NCR, for example, if I have 3 people, I'm choosing 3 people. I know ABC, ACB, BAC, okay, BCA. So this, each one of them is giving me R factorial, 3 factorial. So I'm dividing it by 8. So N choose R is nothing but NPR divided by R factorial, which is giving me N factorial by R factorial into N minus R factorial. So this is what is called the combination. So that becomes very important when you have this N choose R. So suppose I'm choosing 3 people from 50 people. How many ways can I do it? I can do it in 50 choose 3 ways. Would you all agree?
Yes, ma'am.
Yes.
Now choosing
Yes,
3
ma'am.
people
Yes,
from 50 people is the same as not choosing 47 people from 50 people.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes.
Yes.
Would you all agree?
Yes, ma'am.
So how many ways can I not choose 47 people from 50 people?
So
50C
50
47.
choose,
50C 47.
and that is precisely what is this thing. Is it clear?
Yes,
Yes,
ma'am.
yes, ma'am.
Yes.
Right?
Yes, ma'am.
So in
Yes,
the
ma'am.
way is
Yes, ma'am.
selecting R objects is the same as rejecting n minus R from n objects. Okay. Now a very important binomial quantity. Suppose I want to choose R objects from n objects. Okay. Suppose I want to choose from say 50 students, I want to choose 4 students. Okay. Is that clear? Right?
Yes,
I'm fixing one student. So how many ways can I do it? Suppose I fix one of the students. I call that student A. Okay. So how many ways? So I'm choosing from 50. I'm choosing 4 students. There are 2 things. One is A is a part of the 4 people I have chosen, or A is not part of 4 people I have chosen. Would you all agree? I'm choosing 4 people from 50 people. and I know this one person A is a part of this 50 people. Is it clear?
Yes, ma'am.
Yes,
Okay.
ma'am.
Two things
Yes,
can
ma'am.
happen. One is A is a part of these 4 people, or A is not the part of these 4 people. Is that again clear?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay. Now, if A is a part of these 4 people, I know A is one of the 4. How many more should I choose?
3.
3.
3.
And from how many should I choose these 3 people?
49.
49.
49. Because A is already there, so I have only 49 people left. So that would be 49, choose 3. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes,
Now,
ma'am.
if A is not a part of these 4 people, how many people should I choose?
4 people.
4.
4 people.
4 people.
From how many?
49.
Again 49, because A is already out, right? So that is 49, choose 4. And that is what we have here. N, choose R, is the same as N minus 1, choose R minus 1. Okay? Plus N minus 1, choose R. And this is either A is there or A is not there. So that's why it is a plus. Is this clear? How we have just used all the concepts that we have learned so far to come up with a binomial identity. Is this clear?
Yes,
And
ma'am.
please explain the second case.
See, suppose there are 50 people, right? And I know for sure I'm looking, what is your name?
Bhavishya.
Bhavishya. So you are suppose assume that there are 2 things. I'm choosing 4 people. Okay. Bhavishya can be a part of this team or Bhavishya cannot be a part of the team. There are only 2 possible things,
Yes, ma'am.
right? Now suppose you are a part of the team. How many people, how many more should I choose?
3 more.
3 more. How many are these 3 from how many can I choose?
49.
49. So that is
49.
49, choose 3. Agreed? I can
Yes,
do
ma'am.
that in 49, choose 3 ways. Now
Yes, ma'am.
suppose you are not at all there in the team. How many people should I choose?
4.
4
4,
people.
right? And from how many should I choose that?
Should be 50 now. I have to
No,
choose
you're
4
not
people.
there, right? You're not counting yourself. You're not there.
Okay, okay. Okay, ma'am,
So it
clear.
will be 49, right?
Yeah.
This means that the one person is not counted. Is not in the part of selection of the 4 person.
No. That is not what it means. See, the way you should look at it is either this person is in the team or not in the team. If he's in the team, there are so many ways of doing it. If it is not in the team, there are so many ways of doing it. So the total number of ways of doing it is 49C3 plus 49C4.
Yes, ma'am. Ma'am, as you said, in this over 50 students, we are just taking one out. Then we have 49. And there are 2 possibilities. There are 2 possibilities that the one is added among the 4 participants or the one is not added among the 4 participants. If the
Exactly, that is it. So if that person is added in the 4 participants, you can make 49, choose 3 ways of making the choice. If it is not added, it's 49, choose 4. So a total number of ways is 49, choose 3 plus 49, choose 4.
Yes, ma'am. If you choose over 49, if we just the one person is added means we are just considering that remaining 3 positions are there. We are just considering from 49, we are taking out 3.
Yeah.
If he's not added means then also we are just considering of 49 only now. Then
Yeah,
where is the one person?
Because he's not, see, there are only 49 people now. From where will you get the 50th person? Because he's not added. He is there in the overall picture. From where is the 50th person?
We are just removing from account now.
So if you remove him, he's not there. Now you have only 49 people to choose the remaining 4.
Okay, ma'am. Now I got it.
Ma'am, so no matter if we are selecting A for being a part of the 4 students, or if we are selecting or if we are not selecting, but that particular A student is a part of 50 students.
Yes, that's what I'm saying. Yeah. So that's what, see, this is just an example or illustration of this particular binomial identity. Okay, and we are using the concept of OR to actually have the addition here. Is it clear?
Yes.
Okay. So now one of the key things that you will be tested on is when do you have to use a permutation and when do you have to use a combination. Okay. So this is something which many people get very confused about. But just I agree that it is not something that is very intuitive or something, but you keep working on many problems, then you'll get a comfort level with it. So it is very important to distinguish when you have to use permutation and when do you have to use combination. Excuse me, just a second, please. So if the order matters, or if I'm having an order that matters, again, I go back to the example where I say that president, vice president, and secretary. The order matters, whether A is president or A is vice president or A is secretary, that matters. When the order matters, always use a permutation. When the order doesn't matter, use a combination. So let's look at a few examples to just check whether you have to use a permutation or a combination. I want to make a password. Is it a permutation or is it a combination?
Permutation, ma'am.
Permutations.
Combination or combination. Is the order important here?
Yes,
No.
no, ma'am.
Password.
Order is not important, ma'am.
1, 2, 3, 4 is same as 1, 3, 2, 4.
Order is
No,
important.
ma'am.
Password,
I'm asking you, yeah, in a password.
In a
You
password,
all
order is
give. Look at your cell phones. You'll have to give the pin. Is 1, 2, 3, 4 the same as 1, 3, 2, 4?
No.
No,
So is order important or not important?
It's important.
So order is important. Is it a permutation or is it a combination?
It's a permutation.
Permutation.
Getting a feel for it. Okay.
Yes, ma'am.
It is a permutation. Next one. Now, a pizza parlor is offering build your own pizza option. Choice of 5 different toppings from a list of 10 toppings. Okay. How many unique combinations of toppings can be chosen for this pizza? Again, I'm not saying which comes on bottom, which comes on top. That is not. I'm just having toppings, and toppings can be in any way. Is it a permutation or is it a combination?
Combination.
Combination. I just want to choose whether I want corn or capsicum or mushroom or some cheese, right? Or I don't want. So I am building my own pizza. I'm just telling them. So you can see in Swiggy or Zomato, sometimes you have the options, right? And when you're choosing a combo, they'll say, okay, choose any 2. Have you seen that?
Yes, ma'am.
Yes,
So that is a combination. Is that clear?
Yes, ma'am.
This question
Okay.
means that over 10 toppings, we should add 5 toppings in our pizza, right?
But toppings doesn't mean that one year in a pizza you're not adding one on top of the other.
Then, ma'am?
No, that is not how you do a pizza, right? You're just you have a choice of any 5 toppings, which are just randomly placed on the pizza, not one on top of the other. There is no arrangement in this topping.
Yes, ma'am. If we are considering that capsicum, hot dog, cheese, something, etc., etc., over 10, we are just choosing first 5 means that is different from choosing the next 5, right? Then the orders matter, right?
Order doesn't matter. Why should it matter? Okay, let me give you a very simple example. In Swiggy, you are going for a shop and I'm giving you gulab jamun, I'm giving you jalebi, and I'm giving you brownie. Okay, I'm asking you to choose 2 out of 3 sweets. How many? Is it a permutation or is it a combination?
It's a combination.
Combination.
ma'am.
Now, if I give you 10 sweets and ask you to choose 5, is it a permutation or is it a combination?
It's a combination.
Combination.
Toppings why should this how is it different from this problem? In a pizza, if I'm asking you to choose 5 different toppings from 10 toppings.
Okay, ma'am.
It will be a combination, right?
Yes, ma'am.
Is it clear?
One question.
Ma'am, in this choosing gulab jamun and jalebis are same as choosing jalebi and gulab jamun.
Exactly. There's no order. You might prefer gulab jamun over jalebi, but that does not matter here, right?
Yes, ma'am. I know what.
Yeah.
Ma'am, you told in the first question there are 7 character password, but when here mention is permutation 10p4 is equal to 5040. So it should be not 10p7.
Yeah, sorry. Yeah, I'm sorry. Yeah, I agree. Yeah, it should be 4 characters, sir. Okay, so
Yeah, right.
Thank you. Thank you for
ma'am,
pointing
where
it
it
out.
is written, it is not repeated. It can be
I have
repeated
not
also.
written. I should have written that I can. It's not repeated. It should be unique. Okay, I should have written that also. But the bigger thing was whether you are using a permutation or a combination. Okay, I should have made those things more clear. I agree. Yeah.
Ma'am, if then it is not mentioned whether we have to repeat or not repeat, then what concept are we supposed to
No,
use?
in an exam, we'll take care of all these questions. Don't worry. Okay. Yeah.
Ma'am, there was a case in where we want to create a roll number with the numbers. So in the first place, there should be 9 ways, like we can't include 0 because in case of
See,
number.
where it is, if it is specifically mentioned that 0 cannot, for example, a lot of pins allow 0 to be the first number.
Yeah.
Okay. So it will be specifically told to you. You can, unless you're using your assumption of your own, it is specifically told that these things should not happen.
There was a question where it was not specified. So in that case,
I
we will
told
be.
you I'm not going to look at specific questions here, but I think all of you are getting a understanding at a conceptual level. Okay.
That is why I'm asking general question. Like we will be considering the general case where 0 will be considered for the pins.
Unless mentioned that 0 cannot be used in, again, it depends on if I'm asking you to form a 5-digit number. Okay. Right. Instead of a password, I'm asking you to form a 5-digit number. Obviously, 0 cannot be there in the first digit. Would you agree?
Yes, ma'am. Yeah.
Yes.
So I don't have to explicitly mention that.
Yes, ma'am.
So again, it's very contextual. That's what I'm trying to say. If I'm asking you to make a 5-digit number, obviously 0 cannot be here, right?
Yes. Yeah.
So it depends on the context in which but if I'm telling you about a password where 0 is allowed, it will be allowed. Unless I specify that 0 cannot be, it cannot start with 0.
Okay. Clear, ma'am. Thank you.
Yeah.
Ma'am, but there are many questions where it is not specified that whether we have to repeat or not repeat. Then we get confused. What formula are we supposed to use?
See, that's what I said. If it is a 5-digit number or if it is a general thing which is accepted, okay, then you can take it. Otherwise, mostly, if I see even passwords in many cases, they say you cannot start with a 0. Okay. If you have any specific problem where you think that there is an ambiguity, please raise it with the team and they can take care of it. Is that clear?
Yes, ma'am.
Okay. For example, forming a 4-digit PIN code. How many ways can I do?
Ma'am, permutation.
Permutation. Now, is repetition? So here I'm just telling 4-digit PIN code. I'm not telling you whether the repetition is allowed, repetition is not allowed. I'm just telling 4. Imagine for your phone, 4-digit PIN code. How many ways can I do it?
10
Combination.
Is it a combination or is it a
Permutation.
It is
permutation, right? Right.
Permutation.
Ma'am, despite being repetition allowed or not, it's permutation, right?
It is permutation, but then after whether it is repetitions are allowed or not, whether 0 is allowed or not, if 0 is allowed and repetitions are allowed, it will 10 to the power of 4.
Okay.
Right. Now, how would you use in a probability question? The interesting thing is, how many tries would you need to crack a code? How many times? If you write only one, right? What is the chance that you'll get the right code?
1.
1 divided by
10,000.
10 to the power of 4, right? Agreed?
Yes.
Yes,
what is
ma'am.
that chance? The chance is so less, right? Is it clear?
Yes,
So
ma'am.
even if you have to completely enumerate all the 10 to the power of 4 things, so that's why you see, why do you think people have the password tries that it locks after 3 tries?
That it's
The
hard.
chance that you'll get in 3 tries is very low, right?
Yes, ma'am.
It locks your password code within 3 tries. You must have seen a lot of places, right? You keep typing the wrong password, after some time it will lock it. Agreed?
Ma'am.
So it does not allow you to try all the 10 to the power of 4 things so that you get it right. So that is where all your chances and everything, you can work there. Okay, now a bookshelf has 8 different books. Yeah.
Please clear how this is permutation forming a 4-digit pin code. I mean,
okay. 1, 2, 3, 4. This is a code.
yes,
This is a pin code. 2, 1, 3, 4. Is it a pin code?
Okay.
Are they different? I've
Yes.
chosen the same 4
Yes,
numbers
ma'am.
from 10 numbers. Right? Agreed? Yeah.
Ma'am.
So if they have to be distinct, then I'll use a permutation 10p4. If they have to be, I allow repetition, it will be 10 to the power of 4. Because I can have a 1, 1, 1, 1. I could have a 1, 2, 1, 1 and things like that. Is that clear?
Okay, ma'am.
Yes, ma'am.
Okay. Now the fourth question, a bookshelf has 8 different books. I want to arrange 5 books on the shelf. How many ways can they be arranged?
8p5.
8p5 is a permutation. But if I just want to choose 5 books, then is it a permutation or is it a combination?
Combination.
Combination.
Combination. So these are very important. Some of the most popular problems are, for example, when you're choosing teams or forming teams, okay? When you are having the order or the team member roles are very specified, then you use a permutation. For example, a committee of 4 people should be selected from a group of 10 people. Permutation or combination?
Combination.
Combination. But if committee of 4 people to hold specific positions?
Permutation.
Permutation.
Very good. Okay. 4-letter code. Again, it depends. We use only permutation. Okay. So the key point that you need to understand in this permutation and combination topic is when would you use permutation, when would you use combination, and how do you use the correct formula. Okay. Good enough. Is it clear?
Yes, ma'am.
Yes, ma'am.
Let's go on to probability. Okay. Give me 2 minutes.
Ma'am, I have a doubt. If they ask question about selecting and arranging the objects means, then we have to use permutation and combinations both, right?
Can you please repeat?
If they ask question about choosing an object and then arranging, so here we have to use both combination permutations.
In a sense, suppose I say, for example, if I say I choose 4 people, okay,
and they are
right,
arranging and arrange them
then
in a particular order.
Then it's a permutation, right? See, again, go back here. Look at this question. The second question. I am going to have a committee of 4 members. I need a president, vice president, treasurer, and secretary. So I am actually choosing and arranging them only, right? It's a permutation.
I mean, permutation, choosing and arranging both includes.
Yes, that is what the definition is, right? The number of ways I can arrange or I can choose for in an ordered arrangement is permutation, right?
Okay, correct.
Yeah. Okay. So now, so the natural question is, why did we have to learn permutation and combinations? The thing is, whenever we are talking about probability, there is a lot of counting that happens. And permutation and combination, as we see, so far we did not introduce the word probability also. Okay. So probability, why probability? See, one of the main things that we need to understand is we live in a world of uncertainty. Now, when we live in a world of uncertainty, what is happening is we need some tools to handle this uncertainty. Now, what do we mean by uncertainty? Uncertainty is basically when I toss a coin, okay, I know that the outcomes could be a head or a tail. There are only outcomes. So one common mistake people do is probabilities. I do not know what is the outcome. It is not that I do not know the outcome. When I toss a coin, I know there are two possible outcomes. What I do not know is whether it will be a head or a tail. There is an uncertainty about what would be the final outcome. Do you see the difference? Similarly, if I roll a die, I know that what are the set of possible outcomes when I roll a die.
6 outcomes.
It could be any, but I do not know whether it will be one of these 6 outcomes. So there uncertainty. So I define a random experiment as an experiment whose outcome cannot be predicted with certainty. Is it clear what is a random experiment? Some people tell that a random experiment is an experiment with unknown outcomes. It is not an experiment with unknown outcomes. It's an outcome. It's an experiment with uncertain outcomes. I do not know what is the outcome. I cannot predict the outcome with certainty. Is that clear?
Yes, ma'am.
Yes. So now, so that is the next thing is when I know what is a random experiment, the next thing is what is a sample space. A sample space. So one of the way to build this probability was the axiomatic way of building the probability, where you define what is a sample space, and that's why you borrow the theories from set theory. So a sample space is a set or a collection of all basic outcomes. For example, if I roll a die twice, how many outcomes are possible?
36.
36 outcomes. If I toss a coin 3 times,
8 outcomes. It's 8, ma'am.
8 outcomes.
8 outcomes are possible. Okay, right. Now I am going to toss a coin till I get a head. What will be the possible outcomes? I'm going to toss a coin till I get a head. What are the possible outcomes?
3 outcomes.
Ma'am, head, tail, head. It could be many.
I could either, if I get a tail, I could get a head, I stop the outcome. Or I get a tail and then a head, or a tail head, or a tail head. Would you all agree?
Yes, ma'am.
These are the possible outcomes.
Yes.
Is it clear?
Yes,
now, you can see that when I toss a coin 3 times, this is the possible THT, HTT, and so far TTT, 8 possible outcomes. Here I know that there are countable number of outcomes, whereas here you can see that I do not know how many outcomes I have, but nevertheless, both of them are sample sets. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, another thing, let me ask you, the time taken for you to go from your house to college, is that certain or is that uncertain?
Uncertain.
Uncertain.
Is it certain?
No, ma'am.
No.
Certain.
Uncertain.
It's uncertain, right? Now, so what could be the outcomes there? Well, if I ask you to write the sample space, what would be the sample space in that case?
You wouldn't really know in that case.
There is no finite
It could
number.
be anything between 0 and infinity, right?
Yes.
It could be anything between some time. Is that clear?
Yes, ma'am.
It can take, so you can see that the set of all, it could be 1 minute, it could be 1.5 minutes, and whenever you're measuring something, it is a continuous. Whenever you're counting, it is discrete. This is something that we established when we are talking about just numbers also, right? Discrete is count. Measuring is very, continuous, right? Do you count time or do you measure time?
Measure.
Measure time.
Measure. Right? Okay. So you can see that. So that is why we are setting the basis to understand about random variables also, but that will come later. But you can see that sample space can be, for example, of this kind. It can be of this kind and it could be continuous also. Now, another thing is I'm not interested in just knowing about what is the sample space. I might want to know about what is the chance of me getting 2 heads. When I toss a coin 3 times, I might want to know what is the chance of me getting 2 heads. Right? This is something which, for example, let me ask you this question. Suppose head is winning. Okay. Anybody interested in cricket here?
Yes, ma'am.
Yes.
So now the thing is, the England series that is happening, right?
Yes, ma'am.
Okay.
Yes, ma'am.
So suppose I said that both India and England have an equal chance of winning or losing the game. They're playing 5 tests. Forget about all the things that has happened so far. If I ask you what is the chance of India winning 3 out of the 5 tests? Okay. So what are the possible outcomes of this? 5 tests are being played.
Winning first 3 matches, winning first match, third match, fifth match, like that, ma'am.
So how many possible? Suppose we had only 3 matches. Then would you agree that these would have been the possible outcomes? Win, 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 lose, win.
Yes,
Instead of
ma'am.
head, I'll have a win.
Yeah, ma'am.
Instead of tails, I'll have a losing. Agreed? But the context is the same. I have only 2 outcomes and I'm doing the same thing, right? You see that? Similarly, if I have to write 5 papers, what is the chance? And I can pass or fail in each one of them, right? So this is how you can, it is not only tossing a coin, it is the way you can apply that concept to various situations when I have 2 outcomes. Is that clear?
Yes, ma'am.
Right? Okay. So one of the things that we need to understand here is the concept of what we call mutually exclusive outcome. What is mutually exclusive? Suppose I toss a coin again. If I get a head, can I get a tail also at the same time?
No.
Yes, ma'am.
So what is happening is occurrence of one outcome does not allow the other outcome to happen. That is why they are called mutually exclusive. And exhaustive is, can something else happen? When I toss a coin, I can only get a head or tail. Can I get a third result?
No, ma'am.
No, ma'am.
No, ma'am.
So that's what is called exhaustive. So when I talk about a sample set, I need to write all the basic outcomes which are mutually exclusive and are exhaustive. Now, what is an event? An event is a subset of the sample space, or it is a collection of basic events. Okay. Now, why do we need the event? Event, once, this is another building block. For example, an event is a subset. I'm tossing a coin twice. I have head, 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 tail, tail, head, and tail, tail. I can define an event to be head in the first toss. So what are the outcomes that are in this event?
Head, head, and
2
head.
outcomes.
Head, head, and
Head,
tail.
tail.
Head in the second toss is going to be TH and
TH,
right?
HH.
I can label these as events. Okay. So you can see that once I have all these events, this one, I can define a lot of events. For example, head in the first toss, head on the first or the second toss. What would this be? My sample space
Considering both, ma'am, head on the first and head on the second.
So what would that be?
And
It is going to
TH
be
and
HH,
HT.
HT, TH also, right? Head on the first and second toss.
HH.
Yes, going to be HH, right? Okay, so you can see that these are all my events. Now, what do you observe in this event? You can see that this event, head on the first or second toss, is nothing but even union E2. You can see that these 2 events, either head on the first toss or head on the second toss, is what I get here as even union E2, right? And similarly, head on the first and second toss is even intersection E2. And since I have written these as tests, you can see that this becomes a very nice way to describe my events. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes,
Right.
ma'am.
So I can talk, we have talked about disjoint events. The next thing is, let's go back here and define what is a complement of an event. Just as we know what is a complement of a set, what is a complement of event?
The remaining outputs of not.
So what is it? Describe that event. Describe that event. Describe that event.
Sample space minus that event.
And TH.
Describe the event.
TH and
Describe.
TH and TT.
Describe in English.
Everything other than that event.
Subset of an
Not happening that
a
event.
subset of a condition of a event.
If head is on the first toss, what would be the complement of that event? Simple.
It's
Tail on the first toss, right?
On the first toss.
It
Tail
is
on
not
the
on the
first
first
toss
toss.
Head is not on the first.
or tail on the first toss, right? Because here I have only
Yes.
two events, right?
Yes.
What about complement of E2?
Tail on a
Tail
second
on
toss.
first and a second head.
Even complement is tail on the first toss, right? E2 complement is tail on the second toss, which is
Tail on
going to be
first.
HT, TT, right? Okay.
Yes.
What is the complement of E1 union E2? Describe it.
Tail on a
Both
first toss.
tails.
It will be
TT.
E1, union E2.
No, don't talk in math. Talk in English. What is the complement of E1 union E2? I'm
Ma'am,
saying
tail on
that.
first
Both
toss
Tail on
and
a
tail on
first
the
toss.
consecutive toss.
head on both toss.
So tail on both the tosses, right?
Yeah.
Yes, ma'am. TT.
Yes, ma'am.
Yes, ma'am.
E1 union E2 complement is tail on both the
Tail.
tosses, right? Both on, that is the English. You don't have to do the math. That's what I'm saying, which is nothing but tail, right? What is E1 complement intersection E2 complement?
Tail on
Tail on the first
Tail
or
on the
second
At
toss.
least one tail.
and both.
Them, right?
toss.
And you would have seen in your set theory, what is E1 union E2 complement? E1 complement intersection E2 complement?
E2 complement.
Yes. Yes.
Right, that is what we have here. And we are describing this, we are applying this notion to events. Is that clear?
Yes, ma'am.
Yes, ma'am.
Right. And so that is how you can. So one thing which I want you all to start thinking about is to try and describe the events rather than just looking at E1 complement or E2 complement or things of this kind. Start looking at describing the events. That would help you. Look at describing the events. That would help you. Is that clear? Now let's look at some more events. Looked at complement. Okay, so we have looked at these complement events. Now again we have looked at the subsets. Okay. Now the next thing we'll go to this Venn diagram and just what's the time? We have enough time. Yeah. So it's because we are talking about sample space as a universal set. You all know that we can represent the universal set in this way. Agreed?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
And events are subsets here, so I can represent this events as a subset of my sample space. Here I have two events and this is my E1, E intersection F. However, if they are disjoint events, you know that the intersection is going to be not there. Okay, that is what we are going to do. Now this is a subset. E is a complete subset of F. I am going to represent it this way. Now, the main thing is we are not just interested in describing events. We want to assign a chance or probability of that event happening. So the axiomatic approach says that, okay, consider a random experiment. You know how to set up the sample space. Then for every event, okay, I'm associating a number called P of E, which satisfies the following three properties. First is probability lies between 0 or 1. That is the first axiom. The second is because my sample space is exhaustive, the probability of that sample space is equal to 1. What does that mean? One of the event is definitely going to happen. Okay? Because it is exhaustive. When I toss a coin, I know it is going to be head or tail. Some event will happen. It is no chance that nothing is going to happen. And the third is this is a countable union of set is equal to the sum of the probabilities. Now, why are these things important? The first thing is the third event is the probability of union of disjoint events. Even though it is countable, I can talk about a finite union. When I talk about a finite union, I know probability of E1 union E2 is probability of E1 plus probability of E2. This is something that I can talk about. Now the natural question is, okay, you are telling when E1 and E2 are disjoint, probability of E1 union E2 is probability of E1 plus probability of E2. What happens if they are not disjoint? Because you have told me that events need not be disjoint. So let's look at what would happen if they are not disjoint.
Ma'am, excuse me.
Ma'am, can you repeat the probability axiom?
Third
The first
point.
is 0 is less than probability of E is less than 1. The second axiom is probability of S is equal to 1. And the third is the probability of a countable union is the sum of the probabilities. That is the probability of even happening. I can extend that to, I can convert that into a finite union. If E1 and E2 are disjoint, the probability of the union, that is a even or E2 happening, is the sum of the probabilities. Now, what would happen if I have non-disjoint events? For example, let's go back here. Okay, if probability of E union F in this case, what is probability of E union F in this case? If I apply the third axiom,
Probability of
E plus probability of
F. Right. Okay, but in this case, are E and F disjoint?
No.
No.
But
No, ma'am.
if I am going to shade this region, okay, and I call this region E3, I call this region E2, and I call this region E1. Okay, would you all agree that E union F is E1 union E2 union E3?
Yes. Yes, ma'am.
Yes,
ma'am.
Yes, ma'am.
But what do I know about E1, E2, and E3? Are they disjoint?
No,
Yes,
ma'am.
ma'am.
No, ma'am.
Yes, they're not disjoint.
Yes, ma'am.
This is E1.
Yes, ma'am.
This is E2. This is E3. Are they disjoint?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
I agree that probability of E union F is probability of E1 union E2 union E3.
Yes, ma'am.
Now, if I
Yes,
apply the law, what is probability of E1 union probability union E3 from my axiom?
Probability of
Probability of
probability
E1
of
plus
E2
probability of
plus
E2 plus
probability of
probability of
E3.
E3.
Ma'am, that's only the infinity which is shown in axiom 3.
Yeah, the axiom 3 says the probability of the union is the sum of probability provided they are disjoint.
Means how many events we can take, more than
Yeah, I
3.
can take as many probability. That's why I have a countable union. And the axiom says for a countable union, I can use it for a finite union, and it can be as many events as I want. Okay.
Okay.
Now, what is this even? Even is nothing but E minus E intersection E3. Would you all agree?
Yes, ma'am.
So I can write this as probability of E minus probability of E3. And what is E2? Similarly.
E2 minus E3.
E2 minus E3.
E2 minus E3
No,
or
ma'am,
F minus E3?
E3. F minus E3.
E3
Minus.
plus probability of E3. So what do I get? I have a probability of E plus probability of F minus probability of E3.
Yes, ma'am.
But what is E3? What is this area of E3?
Intersection of
F,
E and F.
right?
Intersection of E and F.
Right.
Intersection E and
Probability
F.
of E union F is probability of E plus probability of F minus probability of E intersection F. Do you all agree with me? Now,
Yes.
if E and F are
Yes,
disjoint,
ma'am.
what is E intersection F? If E and F are disjoint,
Probability of F plus
what is E intersection F if E and F are
5.
disjoint?
5.
5.
Five,
But what
ma'am.
is probability of 5?
0.
I have my axiom which only says probability of S is equal to 1. I do not know what is probability of 5. For that, what is probability of S union 5? What is probability of S? It is 1.
1.
1, right? So this is probability of S plus probability of 5. Okay. So probability of 5 is equal to 0 because probability of S union 5 is probability of S. 1 minus 1 is 0. So I get the probability of a complement because probability of E union E complement is probability of S. Agreed?
Yes,
E union E complement.
Yes, ma'am.
Right? But E and E complement are disjoint. So this will
5.
be probability of E plus probability of E complement, which is equal to 1. So probability of any complement is 1 minus probability of that. So probability of 5 is infinity, is 0. So you can see that I can get everything. The probability of a complement is equal to 0, which will give me probability of phi is 0. And that's how I can, using these three axioms, I can generate probability for any union of events, probability of the complement of events and probability of null event. Is that clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Ma'am, I had one doubt, ma'am. May I ask?
Yeah.
Ma'am, why probability of sample space is 1? How does it come?
See, when I toss a coin, what are the possible things that can happen? It is head or tail. Can anything
Head,
else
tail.
happen?
No, ma'am.
So it is exhaustive, right? So
Yes.
the idea of probability of S equal to 1 is telling that when one event is, there is a surely it's going to happen.
Okay, okay.
That's why probability of S equal to 1. You can look at it from that angle. Is that clear?
But ma'am,
Ma'am, I have a doubt. Ma'am, in previous you just said, na ma'am, if I'm just tossing a coin until if I get a head, you are just using counting the values, right? Like if I get at first time itself H, second time TH means what is for that set? What is the complement of it, ma'am?
Good question. But then after, since it is difficult to define the complement. So I could have a head, I could have a TH, I could have a TTH or something of that kind. I'm going to get it this way, right? So what this says, I'm going to keep tossing a coin till, so this will be only the null set in some sense, because I'm having all the things which are, it's a good question. Yeah.
Then we can consider that the complement of this set is in null set.
Yeah, because here what I'm counting is the chance of you getting a head. You're tossing a coin till you're getting a head, right? So
Yes,
I could get a head in the first toss, or I could get a head in the second toss, or I could get a head in the third toss so far. So I cannot define an event that I'm not getting a head at all, right?
Yes, ma'am.
So that's why the complement is a null set. It does not exist.
Yes, ma'am. But I have a doubt, ma'am. We're just considering a set like getting head in the first time, getting head in the second time, getting head in third time, like that until getting head at fifth time. We're just considering a set, ma'am. From that main set, we are just considering a subset like getting a head at third time.
Okay, that is this.
Then what will be the complement of that getting head of third time?
Pardon, I didn't get your question. Yeah, it would be everything else except that thing, right? The complement would be getting head. S minus that. What is complement? This is the entire set. You remove that event, you'll get all the other outcomes in that set.
Yes, ma'am. This means that if we have a different number of sample specimens, we can find the complement of it.
No, the complement of this, see, suppose I define E to be TTH. That's what you're saying, right? What is the complement of E? That is what you're asking. Is my question.
Yes, ma'am.
Right? So that would be this S minus this particular thing. That's what it is. See, complement is S minus E.
Yes, ma'am. Ma'am, from these two examples, can we conclude that if sample space has a definite value means there will be a complement of the set also?
No, I didn't get your question. I'm sorry.
Ma'am, in first question,
see, given a set, I can define the complement of a set, right?
Yes, ma'am.
Then complements exist. So are you asking about the existence of a complement, or what is your question?
Yes, ma'am. I'm just asking the existence of the complement.
It will exist, right? It will either be the null set or it will be some set. It could be an infinite set. It could be a continuous set, depending on how you have defined the original set.
Oh, okay, ma'am. Okay, ma'am.
Okay, is that clear? Yeah?
Yes, ma'am.
Yeah.
Excuse me,
So
ma'am.
this, yeah.
Ma'am, in the axiom 3, does the converse is true?
What is the converse?
Means if the probability of E1 union E2 is equal to probability of E1 plus probability of E2, then we can say that E1 and E2 are disjoint.
If, what are you saying?
And if we prove that the probability of E1 union E2 is equal to probability of E1 plus probability of E2, then can we say that the E1 and E2 are disjoint?
This would mean that they are not necessarily. But why would you want to do it? Where are you just looking at the mathematical thing, or what is the thing? If they are disjoint, it would happen, right?
Yeah. And if this happened, can we say the disjoint converse?
That is, if probability of E1 union E2 is probability of E1 plus probability of E2, then that would mean that your probability of E1 intersection E2 is equal to 0, which would mean E1 intersection E2 is 5. If E1 intersection E2 is 5, they are disjoint, right?
Yes, ma'am.
Yeah.
Okay.
Okay. So let's apply the concepts. So a customer goes into a clothing store. He'll either buy a shirt or, so the question is the following. A customer goes into a clothing store, will buy a shirt with probability 0.3, will buy a pant with probability 0.2 and purchase both with probability 0.1. What is so now the question is, what proportion of customers purchases neither a shirt nor a pant? So I'm defining the events. S is denoting the event that the customer is purchasing a shirt. Okay. So what is probability of S?
0.3.
0.3.
0.3.
0.3. What is the probability of P?
0.2.
So what is the proportion of customers buying neither a shirt nor a pant is the question. So now let's look at, first establish neither a shirt nor a pant is a complement of either a shirt or a pant. So now let's look at only either a shirt or a pant. How would I describe this event?
Union.
This probability is union P. Now, if a person buys a shirt, is the probability of a person buying a shirt mutually exclusive of buying a pant?
No.
No, ma'am.
So what will probability of S union P be?
Probability of S plus probability of P minus probability of
S intersection.
Do I know what is probability of S?
Yeah.
0.2.
0.2 minus 0.1.
What is the probability of the
0.1.
0.1.
So this is 0.4.
0.4.
So this is the probability of either shirt or pant. But that is not what I want. I want neither a shirt or a pant. So what is the complement
of the union?
1 minus probability of union P, which is 0.6. Is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now, the other thing which we always see here is what is called equally likely. For example, when I roll a die, the chance of me getting a 1 is the same as getting a 2. If it's a fair die, it's same as getting a 3. It's same as getting a 6. Okay. Now, suppose you'll have problems like, okay, in the same die, I have 1 on 3 faces, then 2, 3. How many faces do I have remaining? 3 more. I have 2, 3, 4. Is it are all of them equally likely to happen now?
No, ma'am. No.
What is the probability of 1 then?
There are two ones now.
1 by 6.
It's 3 by 6, right?
1 by 6.
1 by
Whereas
6.
probability of 2 is same as probability of 3 is same as probability of 4, which is 1 by
1 by 6.
6. Is it clear?
Yes, ma'am.
But now again, I'm just assuming it's a fair tie. So whenever I have equally likely events, the probability of an event happening is nothing but the number of events divided by the total number of events. And one of the most popular example is to roll a die. If I have defined the event to be an odd number, what is the probability of A happening now?
3 by 6.
3 by 6, which is 1 by 2. B is the event that the outcome is greater than 4. What is the probability of that happening?
2 by 6.
1 by 3.
Okay. I roll a die twice. Okay. What is the chance of me getting the same number on each roll?
1 by 6 by 36.
6 by 36, which is 1. What is the chance of me
Could you
getting?
repeat what you
I
just...
roll a die twice. So how many, what do I have? I have a 1, 1. I have a 1, 2 up to 6, 6, right?
Yes,
Yes.
ma'am.
First, I define the event that both the outcomes are same. So how many outcomes, both the outcomes are same?
6.
6 by 6. So probability of E is 6 by 36, which is 1 by 6. Right?
1 by 6.
Now, I define that the first toss is lesser than the second toss. Lesser or equal to. Okay. How many events do I have now?
15.
Ma'am, what is your question? Can you please repeat?
14.
First toss is less than or equal
Ma'am,
to
21.
Ma'am,
the second.
21.
21 by 36.
Because I'm saying less than or equal to, right? It will be this triangle. Agreed? Okay.
Yes,
So
ma'am.
you can see that you can define events, and since all of them are equally likely, you can find out what is the probability of these events. Is that clear?
Yes, ma'am.
Yes,
Okay.
ma'am.
Ma'am.
Right.
Yes,
So
ma'am.
now the next
Ma'am, one small doubt,
important
ma'am. How
yeah.
to find
Ma'am,
it in
excuse
the
me.
easier way? How they just get to know it is 21 exactly in faster?
Okay, you just noted down 1 1 1 2 1 3. Okay, 1 4 1 5 1 6. Right. Now, how many will I have here? If this is a 2 2, how many will I have here?
4.
It's 4, ma'am.
If this is a 3 3,
3.
this will be 5. This will be 4. This is a 4 4. This will be 3. 5 5. This will be a 2. 6 6 is going to be a 1. What is 1 plus 2 plus 3 plus 4 plus 5 plus 6? You already know that, right?
21.
Yes, ma'am.
Yeah, that's it.
Ma'am, pardon me.
Okay.
Ma'am, pardon, I
Excuse me,
could not
ma'am.
understand, ma'am.
This is 6, right? Number of outcomes here is 6. Agreed?
Yeah. Yes, ma'am.
Number of outcomes here will be
5.
2 2 2 3 2 4 2 5 2 6. I don't have to. This is 6, right? How many will
Yes,
I have
ma'am.
here? 5. Here
5,
with
4,
3.
4.
With this
2.
with 5. With 6 only 1. What is
1.
1 plus 2 plus 3 plus 4 plus 5 plus 6?
21.
That's
21.
it. So you wanted an easy way, right? I gave you an easy way. I don't know whether there's an easier way though. Is it clear?
But in this case,
Yes, ma'am.
first die is greater than the second die, ma'am. In few cases, you
No.
asked, ma'am. You asked
This is
second
2
die.
3 2 4 2 5 2 6 3 3 3 4 3 5 3 6. Always it is lesser, right? I'm only
But you
looking at
asked.
the upper triangle. I'm not looking at the lower.
Yes, ma'am. Yes, ma'am.
Right? I'm looking only at
Excuse
the
me,
upper.
ma'am.
That's why be above. Yeah.
Ma'am, neither A nor B means A complement union B complement, which as per De Morgan's law is equals to A intersection B complement, right?
Pardon?
Neither A nor B, it means A complement union B complement.
Yes.
And which as per De Morgan's law is equals to A intersection B whole complement. Isn't it?
No, can you repeat first?
Ma'am,
I'm saying like neither A, like there was a question here, neither a shirt
Neither,
nor
that's
a
what
pant.
I'm showing neither shirt or a pant.
Yeah. So
Yeah,
it
it is
means
S union P complement.
that is the confusion. I'm saying that neither shirt nor pants shouldn't mean like S complement union P complement individual.
No, it's a NOR, right? So it's S union P. Neither A or B, you look at it as the complement of either A or B.
Okay.
Neither A nor B is either complement of either A or B complement. Is it clear?
Then this is clear.
So
Then
this
what
is
would
A complement intersection B complement.
then what would be the value? What will we say like A complement union B complement? What would we say that?
Pardon?
A complement union B complement. What would be
Neither
that?
A or neither B. That is what it will be.
Okay, neither. Right, clear.
Okay.
Thank you.
Right?
Excuse me, ma'am.
Yeah.
Ma'am, I had that, ma'am, if there is a condition given in the question, like at most or at least, ma'am, in case, the ma'am, the outcomes that would occur in that event would it be excluded from the sample space, or ma'am, would it be there in the sample space, ma'am? Like in the
Anything will be there in the sample space. Nothing is outside the sample space. Everything is in the sample space. Your question
ma'am,
should
like
be, will it be included in the event or not, right?
ma'am, I'm telling for the outcomes which would be occurring in the event.
Yeah, so now let's look at the same thing. I'm tossing a coin twice, right? I'm rolling a die twice. I have 1, 1, 1, 2, 1, 6, up to 6, 6, 36 outcomes. What is the chance of me getting a sum of at least 5? How many outcomes will I can count the number of outcomes, right? And
Yes,
at
ma'am.
least 5 would include, would 1, 3 be included in that?
Yes, no.
No, ma'am.
Will 1, 4 be included?
Yes, ma'am.
Yeah, so that's it. Right, you got it. So you count the number of outcomes, which will give you that.
Ma'am, but in sample space, all the outcomes will be there, right?
I will not include one. Yeah, in the sample space, all the outcomes will be there, but the event will not have all the outcomes.
Okay. Ma'am, for the event, it will be specific and unique.
Yeah, yeah. Not, yeah, but I don't understand what you mean by unique.
Ma'am,
Because all the
mean that,
outcomes, at least 5 would be 1, 4, 1, 5, 1, 6. All of these are going to be this one. Exactly 5 would be only 1, 4 and 4, 1. 2 by 36.
Okay, ma'am. Thank you.
Okay. Right. So now let's move on to the last topic, which is the notion of conditional probability. Okay. So now let's start by tossing a coin.
Excuse me, ma'am.
I know. Yeah.
Ma'am, actually, there's been a lot of confusion on each and every group. I just wanted to confirm that the syllabus for quiz 2 would be week 5 to week 8, right? Or week 1 to week 8?
Swati? Swati, are you there?
Yes, ma'am.
Yes. Can you answer that question?
Can you just repeat?
Ma'am, I'm asking that the week quiz 2 of for stats will have week 1 to week 8 or week 5 to week 8 as the syllabus?
Week 5 to 8.
Okay, thank you, ma'am.
And for the mathematics, please.
Okay. Now, let me continue and then see any administrative question. I would request you to always ask the instructors. They'll know better than me. Okay. I should not confuse you with all whatever the administrator and people who are conducting this or operating this will have better answers. Okay. Please post your question to the right people if you want the right answers. Is that clear?
Ma'am.
Okay.
There's always an official channel. Trust the official channel. Don't trust anything else. Okay. Right.
Okay,
Now
ma'am.
let me move ahead. So suppose I toss a coin once. I know that the outcomes are H and T. I toss a coin twice. I'm going to have HH, HT, TH and TT. Agreed? Okay. Now I want to know what is the chance of me getting a head in the second toss given that there was a head in the first toss. I repeat, what is the chance of you getting a head in the second toss given that there was a head in the first toss? Okay, so forget about probability, forget about everything else. Suppose I give you a coin and ask you to toss it repeatedly. What do you think would be the chance of you getting a head in the second toss given that there was a head in the first toss? Do you think it depends on what was your first toss outcome, or do you think it is independent?
It is independent.
It is independent, right? Okay. Now let me give you another question. So suppose I'm rolling a die again.
Excuse me, ma'am.
Okay. How many outcomes do I have?
Ma'am.
When I roll a die?
6.
6, ma'am.
Okay. I want to know, okay, can I get a sum of 8? Okay. Irrespective of what was my first roll of the die?
No.
No, ma'am.
When can I get a sum of 8? No. When can I get a sum of 8?
When we roll the 2 die.
When first check.
When I roll a 2, I can get a
2,
sum of
3, 4,
8.
5.
3, 4, 5, and 6, right? I cannot, but can I get a roll? What about a sum of 9?
When starting from the 3.
3, 4, 5.
3, 4, 5.
5, 6.
Sum of 7?
Yeah,
It's from 1 to starting from 3, 4, 5. Independent of the
Okay.
first step.
Independent.
So would you all agree with me that to get a sum of 8 depends on what was your first toss, whereas getting a sum of 7 is independent of what was your first toss? Would you all agree?
Yes, ma'am.
Right?
Yes, ma'am.
So when I am having on the same sample space, I have the notion of dependence and independence. Is that clear? Now this says that I have the notion of what is.
Ma'am, can you repeat that 7 1? How do we get it?
Yes, ma'am.
See,
How is it
how do I get
independent?
what are the possibilities of me getting a sum of 7 in this one? If I roll a 1, can I get a sum of 7?
1, 2,
Yes,
3,
ma'am.
4, 5, 6, ma'am.
2, 5, 3, 4, 4, 3, 5, 2,
5,
6,
2,
1. So
6, 1.
I can get a sum of 7 irrespective of what was my first toss. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Whereas a sum of 8,
Yes, ma'am.
if I had my first toss of 1, I can never get a sum of 8.
Yes, ma'am.
Yes.
Right? A sum of 9, I can never get a sum of 9 if my first toss was a 1 or a 2.
Yes, ma'am.
So getting a sum of 8 depends on what was your first toss. Getting a sum of 9 depends on what was your first toss, outcome of your first toss. But whereas getting a sum of 7 is independent of what was your outcome of your first toss. Would you all agree with these statements? Forget about
Yes,
any
ma'am.
math or anything. I just want you to look at it from rolling a dice perspective.
Yes, ma'am.
Yes, ma'am.
Is this clear?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Right? So now if I define an event, you saw that on the sample space, I can define an event of getting a sum of 8. What is the outcome? What are the outcomes that will help me get a sum of, suppose I define event to be getting a sum of 8. What are the outcomes? It would be
2, 6.
2, 6, 3, 5, 4, 4,
5, 3, 4, 4.
5, 3, 6, 2, right? Is that clear?
Yes, ma'am.
Yes,
ma'am.
Yes, ma'am.
Okay. Similarly, but suppose E2 is getting sum of 7, it would be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Agreed? So I can define the probability of events. Okay. So now I want to introduce the notion of conditional probability. So what is conditional probability? Imagine these two. I have E here and I have F here. Okay. I know that F has happened. Okay. So if F has happened, this portion has happened. I want to know what is the chance of E happening given that F has happened. Okay. What is the chance of E happening given that F has happened? F has happened, this would have happened. Would you all agree? Anywhere this would have happened. Now, what is the chance of E happening given F has happened? Would you all agree it would be this yellow, orange portion divided by the total portion of F?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
But what is the orange portion?
Intersection part.
Intersection of E and F.
So you define the conditional probability E conditioned on F to be probability of E intersection F divided by probability F, provided probability of F is, that is probability of F happens, that is greater than 0. This is what is called conditional probability. Now, if this is the conditional probability formula, you know that probability of E intersection F is probability of F into probability of E given F. That is, it says that this is probability of E and F happening, both E and F happening together.
Yes, ma'am.
Right?
Ma'am, excuse
So
me.
that is, pardon?
Ma'am,
So
after E, what's there? E, that one, E, then one line, then F, what it's called?
Pardon?
It's subtraction.
This is a fraction, but this is E conditioned on F. It is not divided by F.
Okay,
The way
okay.
I read this is E conditioned on F has happened. That is why it is called conditional probability. It is defined on a reduced sample space. Okay. For example, if I talk about HH, HT, TH, and TT. F is head in the first toss. HH and HT. Okay. Now E in the first toss. E is head in the second toss. Okay. What is the E head in the second toss? Conditioned on this happening is just HH. Would you all agree? Conditioned on this. So I'm having a reduced sample space. Probability of E happening, conditioned that this has already happened, is just HH. Would you all agree?
Yes, ma'am.
Okay, that is the notion of conditional probability.
Ma'am,
Okay.
exactly what condition, ma'am?
See, suppose I'm tossing a coin and F is the event that head has happened in the first toss.
Yes.
Okay. Now I'm saying what is the chance of head happening in the second toss? Condition that head has happened in the first toss. If I did not condition it, what is the probability of head happening in the second toss?
HH and TH.
TH. Right? Now if I conditioned it, it is only HH. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Okay. Right. Now let's look at this. Now what is from here? What is E intersection F?
HH.
E is head happening in the second toss, which is HH and TH, right? E intersection F is just HH. Would you all agree?
Yes, ma'am.
Yes, ma'am.
And what is the probability of that happening? 1.
Yes, ma'am.
Is it clear?
1/4, I think.
See, probability of E conditioned on F is probability of E intersection F by probability of F. Is it clear? So what
Why
does
we
it mean?
divide both?
Pardon?
Why we divide both?
You're not dividing both. It is probability of, see, if you look at it, F has already happened. Okay. E is happening, given F has happened, is going to be this divided by the entire thing. That's what I'm saying. Probability of E happening given F has happened is E intersection F divided by this entire region. Do you understand? Is it clear?
Yes,
ma'am.
Okay, so it is not dividing. This has to be read as E conditioned on F. E conditioned on F. It is not E divided by F. The definition is probability of E intersection F divided by probability of E of F. Now from here I know what is probability of E intersection F. That is probability of F into probability of E conditioned on F. Till here is it clear?
Yes.
Yes, ma'am.
Right. Now this, just as addition rule was probability for two events, probability of E plus probability of F minus probability of E intersection F. The multiplication rule is on probability E intersection F. Addition rule was on the union. The multiplication rule for two events is on the intersection. And what is that? It is probability of F into probability of E conditioned on F. Till here is it clear?
Yes, ma'am.
Yes, ma'am.
Right? Now, if E is independent of F, okay, what do you think would be the probability of E conditioned on F? What does it mean that E is independent on F? I don't care what F is. E is independent of F. So what would probability of E conditioned on F be? It will be just probability of E. It will be probability of E itself, right?
Yes, ma'am.
Probability
Yes,
of
ma'am.
E. Right?
Excuse me, ma'am. Ma'am, the addition principle here you mentioned just now is a P E plus P F if E and F are disjoint, and multiplication is this that you are telling us right now.
Oh, 1 second. 1 second. 1 second, I think. Just a minute. Just give me a minute. Just Just give me a minute, please. There is some issue. Yeah. Are you able to see my?
Yes.
Are you able to see?
Yes,
Yeah.
ma'am.
Okay. Yeah. So
Yes.
see, what I wanted to tell you was, this is the conditional probability formula, what you see here, right?
Yes.
Is this clear? Now from this
Yes.
formula, I can have probability of E intersection F is probability of F into probability of E conditioned on F, not divided by F. Till here, is it clear?
Yes, ma'am.
Yes,
Right?
ma'am.
What I wanted to tell is, when I looked at additional, it was probability of E union F was probability of E plus probability of F minus probability of E intersection F. This was the addition rule, not about disjoint union. If it was disjoint, this was 0, then it would have been sum of probabilities. Is that clear?
Yes, ma'am. Yes, ma'am.
But this is the general addition rule. Just as I had a general addition rule, I have what is called the general multiplication rule for two events, which is probability of E intersection F is probability of F into probability of E conditioned on F. Till here, is it clear?
Yes, ma'am.
Now, if E is independent of F, just the notion, suppose E conditioned on F, suppose event E is independent on F. My question was, what is probability of E conditioned on F? Without any math, just tell me, if E is independent, E happens does not depend on whether F has happened or not. Then what would be the probability of E conditioned on F?
Probability of
It would be probability of E itself, right? Yeah?
Yes.
So what would happen to this? This would be probability of E. Agreed? Which
Why
would
not
say that the
probability of
probability
F in that case?
of F is there, already there. I'm only talking about the condition probability here. E has nothing to do with F. Okay? F is there, right? We are only talking about E conditioned on F. F is existing. So the rule states that the probability of E and F occurs is probability of E into probability of E conditioned on F. So what would happen is, when I have E is independent on F, this reduces to probability of E, giving me probability of E intersection F is the product of probability. So in the addition rule, when I had disjoint, probability of E union F was probability of E plus probability of F for disjoint and mutually exclusive. Similarly, E is independent of probability of E intersection F is probability of F into probability of E. So I can define this as probability of E intersection F. If probability of E intersection F is the product of probability, then they are independent. This is an if and only condition for only two events. What is the multiplication rule? If E and F are independent, the probability of the intersection is product of the probabilities. This is for two events. For three events, it is slightly more complicated because I have a generalized multiplication rule. But for more than two events, you can refer to the notes. But this is what, when I'm talking about multiplication rule, the conditional probability plays a big role. So let me just show this probability tree and finish with that. So I have tossing a coin once, I have head or tail. If I toss a coin twice, you can see that I have, if it is a head, I have a head and a tail again. I have a head and a tail again. What is the chance of me getting a head in the first toss?
1 by 2.
It's a fair toss.
1 by 2.
This is
1
half
by
and
2.
half.
1 by 2.
Here, what
1
is the
by
chance
2.
of me getting a head in the second toss? Suppose I
1 by
start from
4.
here. This
1
is
by
also
4.
a half.
1 by 4.
This is also a half. This is a half. This is a half. So what is the chance of me getting a head and a head? It is
1
head.
by 4.
Because getting
1
a
by
head in
4.
the second toss is independent of this. This is going to be 1 by 4. This will again be 1 by 4. This will again be 1 by 4. This will again be 1 by 4. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes.
Now let's look at this. Okay. I have a bag of 4 white and 3 blue balls. What is the chance of me getting a black ball? 4 white and 3 black balls. I'm picking up one ball. What is the chance of me getting a black ball?
3 by 7.
3 by 7.
3 by 7.
3 by
What is
7.
the chance of me getting a white ball?
4 by
4 by
7.
7.
4 by 7.
If I get a black ball, I'm going to go to bag 2. Okay. Where I have 3 white and 6 black balls. Now what is the chance of me getting a black ball?
6 by 9.
6 by 9. White ball?
3 by
9.
9.
1
by
by
9.
1 by
3 by 9.
3 by 9, right? Is it clear? Now here, if I get a white ball, I go to a second bag. I call it bag 3 with 4 white.
4 by 9.
So what is it? This is going to be
4 by 9.
4 by 9.
4 by 9.
White, sorry,
5 by
black ball
9.
is going to be
5 by
9.
9.
5 by 9. This will be 4 by 9. So what is the chance of you getting both black balls?
3 by 7.
3 by 7 into
2 by 3.
6 by 9.
6 by 9.
6 by 9.
Right? This is 3 by 7 into 3 by 9. But what I want you to see here is the chance of you getting a black ball in the second draw depends on whether you had a black or a white ball in the first toss. Do you agree? Because this is 6 by 9 and this is 5 by 9. They are not the same.
Ma'am, can you repeat what you said right now?
See, would you all agree that the chance of me getting a black ball here is 6 by 9?
Yes, ma'am.
Yes, ma'am.
What is the chance of me getting a black ball here?
5 by 9.
So the chance of you getting a black ball this is the second draw. This is the first draw, right? The chance of you getting a black ball in the second draw depends on whether you had a black or a white ball in the first draw. Would you all agree?
Yes.
No, ma'am.
Why not?
It depends.
This is 6 by 9, this is 5 by 9. Similarly, the
Yes,
chance
ma'am.
of you getting a white ball here is 3 by 9, here it is 4 by 9.
Bag 1 and bag 2 are separate bags.
Yeah, they are different, right? I'm saying if you get a black ball, you are going to bag 2. If you get a white ball, you are going to bag 3. This is just an experiment I'm setting up.
Okay, ma'am.
Okay, ma'am.
Or you can look at it. Okay, if you don't like bag 1 and bag 2, I'm saying that you are not replacing the bag. So if you get a black ball, how many balls are left now? You're not replacing it. How many balls are left?
4 white and 2 black.
4 white and 2 black.
6 balls.
Here, how many are left?
3 white, 3 black.
3 white, 3 black.
Now, what is the chance of you getting a black ball in the second draw now?
2 by 6.
2 by 6.
What is the chance of you getting a black ball here?
4 by 6.
4 by 6.
3 by 6, right?
3 by 6.
3 by 6.
3 by 6.
Yeah.
Are they same?
No, ma'am.
So the
No.
chance of you getting a black ball in the second toss, second draw, depends on whether you picked up a black or a white ball in the first draw. That's what I want you to say.
Yes,
So they're
ma'am.
dependent
Yes.
events.
Yes, it depends.
Okay. Whereas here the chance of you getting a head or a tail in the second toss was independent of whether you are getting a head or tail in the first toss.
Yes,
Yes,
ma'am.
ma'am.
Clear.
Even
Yes,
though they are
Yes.
very similar. Okay. So this is what I want you to understand when you're talking about dependent or independent events. You can draw this kind of what is called probability trees and get it. Is it clear?
Ma'am.
Ma'am,
Yes, ma'am.
I didn't get it how both are dependent. In the previous
Okay, let's
yes, ma'am,
look
in
at
this
this. Instead of
example.
let's start this, okay? Let me define another thing. I have a bag. How many balls do I have? 4 white and 3 black balls. Till here, is it clear?
Yes, ma'am.
Yes,
Now I'm
ma'am.
picking a black ball. What is the chance of me picking? Let me call it B1 and W1. Okay. What is B1? B1 is the chance of you finding a black ball in the first draw.
3 by 7.
3
Okay,
by
what is
7.
the probability of B1? It is 3 by 7. Till here, is it
3 by 7.
clear?
Yes.
Now, if it is a black ball, I set the black ball separately. So, how many balls do I have remaining?
4
4.
white, 2 black.
4 white and 2 black, right? Now, in the
Yes.
second draw, what is the chance of me picking up a black ball?
2 by 6.
2 by 6. What is the
2
chance
by
of me picking up a white ball?
4 by 6.
4 by 6. So, if I have a B1, B2 and a B1, W2, okay, this is 3 by 7 into 4 by 6, 2 by 6. Would you all
Yes.
agree?
ma'am.
Whereas this is going to be 3 by 7 into 4 by 6. Is that right?
Yes,
Yes.
ma'am. Ma'am.
Right. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, suppose I have here 4 white and 3 ball. This is 4 by 7. What is the chance of me picking up a black ball in the second toss? I have 3 white and 3 black remaining, right? What is
Yes,
the
ma'am.
chance of me picking? This will be 3 by 6,
3 by
Yes.
6.
3
3
by
by
6.
6.
right? So what I'm trying to say is the probability of B2 happening given B1 is not the same as probability of B2 happening given W1.
Yes.
Yes, ma'am.
So the probability of me getting a black ball in the second toss or second draw depends on whether it was a black or a white ball in the first draw. It is different.
Yes,
So
ma'am.
black ball is dependent on what was your first draw. Is that clear?
Yes, ma'am.
Yes,
Could
ma'am.
you repeat it?
Ma'am, it was
Getting a black ball. Yeah, please.
ma'am,
what
it
is the
was
question?
because ma'am, I think if we are replacing it, if we
If
are
you're replacing it, it's different. I'm saying it is without replacement. The
okay.
experiment is without replacement. If you're replacing it, it would continue to be 4W and 3B, 4W and 3B. It's the
Then
same.
it yes, ma'am.
Then
Then
it is independent. But if you are
okay.
not replacing, it is dependent.
Yes, ma'am.
You get it?
Yes,
Yes,
If you're
ma'am.
replacing it, it is the same as tossing a coin. It is a biased coin here in some sense, right? Because it will remain the same. But if it is without replacement, it would be dependent events. That's what I wanted to tell. Is
Yes,
that
ma'am.
clear?
Got yes, ma'am.
Yes, ma'am.
Yeah.
Ma'am, can
And
you
if
please
we
repeat the last
Repeat
statement?
what? See,
That
suppose
if
let
we
me
are
look at.
yeah.
See, suppose I have 4 black, 4 white, 3 black balls in this bag. Okay. I am drawing one ball. What are the possible outcomes?
Either white or either black.
What is the chance of it being white, black?
3 by 7.
3 by 7.
What is the chance of it being white?
4 by
4
7.
by
7.
4 by 7.
Now I'm not replacing it in the bag. So if it is a black ball, how many balls will I have remaining?
White.
2 white and 2 black.
Now what is, again I'm
Excuse
picking
me,
up a
ma'am.
ball from here. What is the probability of picking up a black ball?
2 by 6.
2 by 6.
What is the probability of picking up a white ball?
4 by 6.
4 by 6.
Now again here, if it is a white ball, how many I have remaining?
3 white and 3 black.
3 black.
What is the chance of me picking up a black ball?
3 by 6.
By 6.
What is the chance of me picking up a white ball?
3 by
3 by
6.
6.
by
6.
So what is the chance of you getting a white ball in the second draw? Does that depend on whether you picked up a black or white ball in the first draw? Or is this independent?
Yes.
Dependent.
Depends.
Depends.
So that's what I'm trying to say. Whereas in tossing a coin, whether you get a head in the second is independent of whether you had a head in the first toss or not.
Yeah.
Okay, do you get it now?
Yes.
Okay.
Please explain. You have taken the bag 2 and bag 3.
It's the same thing. It is just a different experiment here.
So if you
I'm
take
saying
bag
that
2
if
and
you
bag 3,
get a
it's
black, you go
dependent.
to bag 2. If you get a white, you go to bag 3. That's all.
If you take bag 2 and bag 3, then also it is dependent.
Yeah, this is also dependent. I'm just saying if you get a black, you go to bag 2. If you get a white, go to bag 3. I can define that experiment anyway. Again, here you can see how do I get this? So if you look at it, you can see that the probability of B1 intersection B2 is nothing but probability of B2 given B1 into probability of B1. That is how we have got it. Is that clear?
Yes, ma'am.
Okay. So that is about the
Had one
notion
doubt.
of. Pardon?
Ma'am, what if we take 2 balls at a time?
Take it now, then you can work it out. You take it, you do it. If you understand it at the conceptual level, you do it. And see what is the answer you're getting. Okay. Now I think I am running out of time, so I'll do the last thing, which is base theorem, and I will wrap it up. Okay, we are already 10 minutes ahead. No, I'm sorry. I think I'll just go to the. It's already we are overshot by 10 minutes. I'll just talk about what is base theorem. See, suppose I have my events in this case. So let's look motivated from this example. Okay. Imagine that I'm getting shock absorbers from 3 companies. Okay. So this is, I'm getting 100 shock absorbers, of which 20 come from A, 30 come from B, and 50 come from C. Okay. So now I take one shock absorber at random to a company. I am having 100 shock absorbers, 20 come from A, 30 come from B, and 50 come from C. I take one shock absorber at random, okay, and I want to know then what is the chance that it has come from A?
20 out of
0.2, 20 by 100, which is 0.2, right?
Yes.
Agreed?
Yes,
What is the
ma'am.
chance it comes
Yes,
from
ma'am.
B? That is
0.3.
0.3.
What is the chance it comes from C?
0.5.
It is 0.5. Till here it is clear?
Yes, ma'am.
Yes,
Now,
Yes,
out of these 100, I could have defective. What they are telling is the percentage of defective items produced by A is 3%, D is 2%, and C is 1%. So, out of these 100, I have defectives which are coming from everything. I could have defectives from A, this is defectives from B, this is defectives from C. This is the defective lot. This entire thing is good lot, this is the defective lot. Till here is it clear? This is my D.
Yes,
Is
ma'am.
that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So can I write this D as D intersection A plus D intersection B plus D intersection C? Would you all agree that I can write it this way?
Yes, ma'am.
Yes.
Now, are these this D intersection A, D intersection B, and D intersection C are disjoint?
Yes, ma'am.
Yes, ma'am.
So I can write the probability of a defective is probability of D intersection A plus probability of D intersection B plus probability of D intersection C. Till here, would you all agree?
Yes,
Can
ma'am.
you
Ma'am.
please explain how you
So
write
now
the equation for D?
let me go back. I pick up an item and I notice I want to know what is the chance that it is defective. That is my question. So what is probability of D? You pick up an item, you want to know what is the probability it is defective. Is that clear? Until here you are all clear, right? How I got this?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
What does the conditional probability theorem say? Probability of D intersection A is probability of D conditioned on A into probability of A. This is probability of D conditioned on B into probability of B. This is probability of D conditioned on C into probability of C. Agreed?
Yes, ma'am.
Yes,
So you
ma'am.
know what is probability of A? 0.2.
0.2.
Probability of B?
0.3.
Probability of C is 0.5.
0.5.
What is probability of D conditioned on A? It is saying what is the chance that I know an item is coming from factory A. What is the chance that it will be defective?
0.03.
That is given by this, right? What is this 3%? It is the percentage of defective items produced by A, which is probability that it is defective given it is from A. Agreed?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Similarly, what is probability of D conditioned on B?
Yes, 0.0.
2%.
0.02. What is the probability of D conditioned on C?
0.01.
So this probability, I can compute this, right? Which is 0.03 into 0.2 plus 0.02 into 0.3 plus 0.01 into 0.5. That is the probability that a randomly chosen shock absorber will be defective. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Now, this law is what we call the law of total probability. That is, if I have mutually exclusive events and an event which is like this, then the probability of this event happening is probability of D given A into probability of A plus probability of D given B into probability of B plus probability of D given C into probability of C. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am. Yes,
Now, the second problem is, I know something is defective. I pick up an item at random. Initially, I asked you the question, what is the chance that that item comes from factory A? You told me it's 0.2. Okay. Now I'm repeating the same thing. I'm picking up an item, but I'm noticing it is defective. Okay. I'm asking you now, what is the chance that it comes from factory A? So what is it? What is given to me? What is the information that is given to me?
Factory A.
It is defective, right?
It is defective.
I want to know what is the probability A given it is defective. See, earlier when I just picked up an item, I knew probability of A is 0.2. But now I have some additional information on it. And what is the additional information I have? The additional information I have is it is defective. Do you get it?
Yes, ma'am.
So now I want to know what is
ma'am.
probability of A given D. What is probability of A given D? From my definition, it is probability of A intersection D divided by probability of D.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now this is nothing but probability of D given A into probability of A. I already know what is probability of D, right? So that is
Yes.
what is Bayes' theorem. Okay, Bayes' theorem says that this is probability of A intersection B given B, and this is what I have. This is the law of total probability, and I can compute this for any number of events. If this is not 2 events or 3 events, as long as I have F events which are mutually exclusive, then I can define what is Bayes' theorem, and I can use Bayes' theorem. So whenever I have to use Bayes' theorem, the key thing is to first identify what are the mutually exclusive events, what is this event D, and then how do I use the posterior probability. This is what Bayes' theorem is about. Okay. I think I'll stop here. We are already 20 minutes ahead. Okay. I hope you all found it useful. Wish you all the best.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank
you, ma'am.
Thank you all.
Thank you, ma'am.
And, yeah.
Thank
Okay.
you.
Thank you so much, ma'am.
Thank you. Thank you.
Thank you, ma'am.
Thank you. Good night and thank you. Take care. Do well.
Thank you, ma'am. Good night.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yeah.
Ma'am, can you share this PPT in the chat section?
Yeah, I will not in the chat section. I'll give it to Swati and she'll put it on the Swati, I'll share it with you, okay?
Yes, ma'am.
I'm on discourse.
No,
Wherever
we will
she
just
puts
put
it.
it into supplementary content, like the other live session.
Okay, ma'am. Thank you.
Okay, ma'am.
Thank you, ma'am.
Swati, just put a watermark before you share it.
Sorry?
Just put a watermark before you share it, okay?
Okay, ma'am.
Otherwise, you start finding all these PPTs in every website. I don't want that to happen, okay?
Okay, ma'am. Sure.
Right. Thank you.
Ma'am,
Okay,
so
then.
where should I check it?
Pardon?
Where should I check? Where should I check the link for the PPT?
I think
No, it will
Swati
be.
already told that she'll do it.
Yeah, I will be uploading it in the supplementary content.
Okay.
Okay, ma'am.
Ma'am,
Thank you, ma'am.
Yeah.
Okay, ma'am.
ma'am, I have a short conceptual doubt, ma'am.
Okay. Well, last question, okay? Because you're already yeah. Go ahead.
Ma'am, how can we identify that whether a selection is simultaneous or not?
Swati, can you take this in, because this would be needing a particular example. So can you take this up in the
Next session.
tutorial
Yes, ma'am.
or in the discussion?
Yes, ma'am. Sure.
Okay, they will do it in that. Okay, they'll take it with an example and they'll do it. Okay, right. Thank
Okay,
you
ma'am.
all.
Thank you.
Good night. Yeah.
Thank
you
you,
all.
ma'am.
Bye.
Good night, ma'am.
Good night. Good night.
Thank you, ma'am.
Thank you.
Thank you, ma'am. Good night.
Good night.